Okay, welcome to second semester chemistry, and let's talk about liquids and solids. All right, so this should be something you probably learned in kindergarten even. Let's just take a comparison look at gases, liquids, and solids. Right, we know that gases are something that that are fluid, so they're movable. And this is because their molecules are widely separated. We can compress gases down into a smaller container. Liquids are fluids also. They are relatively incompressible. If you've ever tried to add more water to a bottle and then put a cap on it, you know that you can't compress it down much further, but they are, and that's because the molecules are more tightly packed. However, it is still fluid, and so that it moves and fills the container. And then solids are nearly incompressible, and we know they're rigid and they're not really fluid. And their molecules are or ions are very tightly packed and in close contact. So here's a good representation. So gas molecules are far apart, and they can move in all kinds of directions, and they fill the container fully. Liquids are also fluid. They have some space in between them, and so they can move past each other, but they don't, you can't compress them very much. And then of course solids are rigid and and liquids we know fill the container to the extent that they can, so they don't expand to fill the container, but they take the shape of the container. And then of course solids have their own shape. If you're wanting to look at these videos, they're just kind of showing these kind of things too. All right, so let's talk about why are there different states of substances and what's happening when we have solids, liquids, and gases. Okay, so we know that the state of the substance will depend on the balance between kinetic energy of particles. So we know that all molecules are moving. They all have some kind of kinetic energy. So there's this balance between the energy of motion of the molecules versus the intermolecular energy. So attractions that hold molecules together. So it's a balance. So intermolecular attractions, again, are the forces of attraction that exist between atoms and molecules, or ions too. So that's what holds them close to one another. And then of course the kinetic energy is what keeps molecules moving past each other. So again, it's that balance. If the intermolecular attractions are really strong and the kinetic energy is low, then they're going to be held really close together. However, if the kinetic energy is high and the attractions are very weak, then you're going to be in the gaseous phase and the molecules will be far apart. So it's that balance. So because obviously a water molecule is a water molecule. So whether it's in the solid, liquid, or gaseous state depends on how much energy the molecule has, or in other words, the temperature. So we'll look at that in a minute. So again, yep, kinetic energy depends on the temperature. If we increase the temperature, we increase kinetic energy. And so that by heating it, we give it more kinetic energy. By cooling it, we lower the kinetic energy. So that's why temperature is sort of the main factor for whether we have a solid, liquid, or gas. And just as a note, intramolecular forces. So if you see the intra, that just means within the molecule. So those are like if you have got my little pen here, I forget that I could write on it. So if you have like a H2O molecule, right, an intramolecular force are the bonds here between the O's and the H's. But then the intermolecular attractions will be ones that are happening here between molecules. So this is intermolecular. Let's change the color here. And this is intramolecular. Just so you keep that straight. So this is between molecules. So we're talking about these intermolecular attractions in between. You can keep that straight. Interstate means roads that connect states, so between states, and then like something like intramurals means, you know, you're having the sports just within your organization, so just within the molecule. Okay, so here's a good picture too. So here's again, intramolecular is the bond here within the molecule, and that's always a strong force. That's holding the molecule together. An intermolecular force, then again, are the bonds or the attractions between molecules. They can be strong. They tend to be weaker than the intramolecular forces. So just keep that in mind. This chapter, we're talking about the nope, take that back. This chapter, we're dealing with the intermolecular forces. All right, so we know what a gas is. A gas is a collection of widely separated molecules, and they're in constant chaotic motion. So generally speaking, at least relatively speaking, gases tend to be at higher temperatures. And of course, it depends on the molecule itself, but on the scheme of things, within the same molecule, gases tend to happen at higher temperatures. So the average kinetic energy of the molecules is going to be much higher than the average energy of attraction. So as long as they're moving fast enough so that those attractions are not very important, you're in the gaseous phase. So that's why there's the lack of attractive forces that allows the gas to expand to fill the container, and that's why gas laws hold regardless of the identity of the gas, because we assume in our gas laws that the attractions are very slim, between molecules are very slow, if you remember that from last semester. So so the attractions are low and the kinetic energy is high. So liquids, of course, fall in the middle. The intermolecular attractive forces now are strong enough to hold the molecules close together. And again, it's not that the attractive forces change, it's just that you imagine if you've cooled a gas down, they're moving slower, so now if they come close to each other, the attraction takes over and it becomes more important, and that's because the molecules are moving slower. So the balance has switched. So like I said, if you've got two water molecules, the attraction between them is not going to change. It's how fast the molecules are moving in order to avoid being trapped by each other. So liquids are therefore much denser because they have, or they're more dense because they are, they're much closer to each other, so there's less space between them. They're less compressible, again, because there's less space between them. And in this case, the intermolecular attractive forces are not quite strong enough to keep the molecules from moving past each other. However, they are strong enough to hold them close to each other. So that's why liquids are still more random than solids. There is still some movement because the balance hasn't totally shifted. And so, of course, solids, then, the intermolecular attractive forces are now strong enough to hold molecules close together and actually lock them into place. So that's why they're rigid. Solids are not compressible because there's very little space between the molecules, and they tend to often form highly regular crystalline patterns, which we'll talk about at the end of this chapter. And again, remember, what's the difference between a liquid and a solid? You tend to remove energy by lowering the temperature. So again, the molecules are moving much slower, and that's why the attractive forces can take over. However, just keep in mind that solids still have some thermal energy, and so they do vibrate in place. There is still some movement. The only time that you have no movement at all of any molecules is not until you get down to 0 Kelvin, absolute zero. And actually, that's not been achieved. They've gotten very close, but they've not actually gotten anything down to absolute zero. All right, so this picture just sort of shows some of the difference. So you can see again the intermolecular forces, the importance of them are increasing as you go to the left, and so the stronger the forces, the more likely you are in a solid. And then if you increase the temperature, the balance shifts. And so again, it doesn't mean if it's the same molecule, the attractions are still the same. It's just now the molecules have enough energy to pull apart from each other and not be kind of trapped with each other. So that's why the gas, they're still the same molecules. They're just moving fast enough to avoid the interactions. And just so that's kind of a good view there. All right, so again, let's talk about what are intermolecular forces. So they are the forces of attraction between molecules, and there's actually different kinds of intermolecular forces. 3 types that we're going to discuss are dipole-dipole forces, hydrogen bonding forces, and London, or sometimes called dispersion forces. We also can include ionic forces. Ionic forces are, of course, between ions. So in this discussion right now, we're mostly going to just be talking about the non-ionic forces. So dipole-dipole, hydrogen bonding, and London, or dispersion forces. So let's talk about them individually. All right. So a dipole-dipole force happens when you have a polar molecule, and we talked about polar molecules in the last chapter, last semester. And so again, if you have a polar molecule, what that means is one end is a little bit more negative, one end is a little bit more positive. It's not a full ion, so it's not ionic. However, because one end is more negative, when you line up the molecules, it's attracted to the positive end of a neighboring molecule, and then the negative is attracted to another positive side of an ion. So they kind of line up. So you can see here they're lined up into head to tail. This one, this can happen too, where you have one end attracted where they're kind of inverted. And of course, there may be some interactions here, and there might be another one with the positive here and the negative here, and so there's all kinds of attractions, and they're being held together. So these are called dipole-dipole forces because they happen between dipoles. Polar, polar, dipole means 2 poles, right? So it's got the two poles of the object. One end is positive, one end is negative. So that's where dipole comes from. It's a polar force or a dipolar force. So that happens when you have polar molecules. You will always have dipole-dipole forces. So dipole-dipole force is an attractive intermolecular force from the tendency of polar molecules to line themselves up, positive end to negative end. So that's what I just said. And this shows the arrangement of it. Okay, here's another picture. So this is showing, so you can see, like, if something is solid, they tend to be a little bit more regular, and so you can see that they're really kind of rigidly lined up, whereas a liquid, there may be some a little bit closer, a little more random, but once it cools down even more, it becomes more rigid. But anyway, these are all dipole-dipole or polar dipole-dipole forces, and they happen only with polar molecules. Okay, so what is hydrogen bonding? And just here, just keep in mind that hydrogen bond is actually a misnomer. Is technically not a bond in the way that we talk about bonds like covalent or ionic bonds. So it is, but it's still considered an intermolecular attraction. So it's still between molecules. We call it a bond, but it's a little bit not quite. So it's a special type of dipole-dipole interaction. And it's called hydrogen because it only happens when you have molecules that have an HF bond or an HO bond or an HN bond. And if you look at your periodic table, or if you look at electronegativities, remember that when you've got your periodic table, electronegativities are the highest right here. So fluorine, actually noble gases are not included, but like fluorine is the highest electronegativity of all the elements, and then oxygen and nitrogen. So they're all right here. Sometimes you could include chlorine too, but they tend to only talk about the nitrogen, oxygen, and fluorine. So what happens is because the N and the O and the F have the highest electronegativity, these are the most polar, or the most so the dipole is the biggest. So these are, very polar, so very negative, and then the hydrogen is positive. So it's the biggest difference between electronegativities, making these very polar molecules. So that's the first thing, because N, O, or F have very high electronegativity. They're very they're going to be very polar molecules. And then the other thing has to do with hydrogen. So here, hydrogen are very tiny. So you've got this very tiny atom, and then a very much larger atom that's very negative. And so it makes what happens, and when you get them close to each other, so let's say you had a different water molecule here. So there's an attraction here again between the negative oxygen and the positive hydrogen. Because it's so polar and because the hydrogen is so small, it can get really close. It makes for a very tight dipole-dipole interaction, and that's why it's given its own name, hydrogen bonding. So it is a dipole-dipole interaction, but it's specifically to an OH, NH, or FH. So if you don't have the H and if you don't have the N or F, then it's just considered a dipole-dipole interaction. So hydrogen bonding is just these. So this just shows, so this is water, for example. This is why water is such interesting, and we'll talk about that at the end of this chapter, why water is such an important molecule, and why it's, even though it's so tiny, it's very polar. The hydrogen bonding occurs between molecules, and again, it's because the O is so negative and the H is so tiny. So there's a very strong attraction between the H atom and the O on a neighboring molecule. So here you can see some of the hydrogen bonding. So you've got a strong attraction between the H's and the O's on neighboring molecules. Now, when it's a liquid, they're further apart, and as you cool them down, these interactions become even stronger, and so you can get the solid where they're holding it together. But again, these interactions are still weaker than covalent bonds. However, they are the strongest of all intermolecular forces. So hydrogen bonding is the strongest type of dipole-dipole. And we haven't talked about dispersion yet, so that's the weakest. So again, why is that? It only happens with O, N, or F, and it has to be specifically attached to an H. It's because these are the most electronegative, and H is the smallest, and so it can move in really close and make a really strong interaction. It's just pointing out that hydrogen bonding is very, very important biologically. For example, this is two specific bases that make up DNA, and you can see here that hydrogen, so a hydrogen bond will occur. It doesn't have to be the same molecule, so it has to be the OH, the NH, and the FH, and then it has to be attracted to another O, N, or F. So you can see here, let me use a different color, the O, it could be between an O of any kind and an H that's attached to either an N, O, or F. And so here you can see that here's an N attracted to an H, here's an H attracted to an O. So the H has to be attached to an N, O, or F, as you can see here. And then it has to be attracted to another O, N, or F, and that makes it a hydrogen bond. And so you can see that actually that's what attracts DNA, or what holds DNA together, are these hydrogen bonding. So it's a really important. It's also what makes water. We'll talk about this later. Water is a liquid at room temperature, which is actually very unusual for such a small molecule. It should normally be a gas, but it's a liquid at normal room temperatures, and this is because of hydrogen bonding. So finally, the lowest, the weakest kind of intermolecular interaction is called a London dispersion forces. Sometimes you'll just hear them called London forces. Sometimes you'll just hear them called dispersion forces. Sometimes you'll hear London dispersion forces. So any of those three words will work. But they are the weak attractive forces, and this happens if you have a non-polar molecule. So if you got just a regular old molecule that doesn't have a positive end or a negative end, there may be, at first you might think, well, there's no interaction between them. However, there are what's called instantaneous dipoles. They just occur randomly, and they occur, as this says, instantaneously. And so what happens is, so let's say, I'm going to use a different color here. Go back to my, can't find my marker. Okay, there we go. All right, so let's say we have a molecule, and it's not positive or negative. It's not polar at all. And we know, remember, polar just means, or non-polar just means that they're sharing the bond, whatever the two, let's say it's a nitrogen and a nitrogen, and so they're the same element, and so the electrons are shared between them very evenly, so we don't have a dipole, we don't have a positive or negative end. But what happens is sometimes just instantaneously, because electrons are all hanging around, maybe for just a very short instant, all the electrons end up on one side, making this side a little bit negative, and because this side is lacking them, it might be a little bit positive just for an instant. So now if you've got a neighboring molecule here, at that instant in time, because this end is a little bit more negative, it's going to push the electrons away, and it's going to induce a dipole in the neighbor. But when that happens, this is already long gone. So this is back to normal, but it induces this dipole, and so then it induces a dipole here, but that one's long gone. So it's got these really tiny little interactions between molecules that kind of appear and then disappear. So they are holding together, but just very, very weakly. So kind of like if you're at a football game and you know the wave, somebody starts a wave over here, the next person responds, but they're already done with it. And so it kind of moves along. And so it's just this like this fleeting, fleeting little attraction between molecules. So it's not very strong. And so that's where we get this induced dipole, that it doesn't last, but it's there to hold molecules together weakly. Let's see if I can erase this so you can read that. Okay, so again, a couple of things to know about these London dispersion forces. The bigger the molecule that you have, the more likely that you can have dispersion forces. because you have more electrons. So the bigger the molecule is, the more electrons you have, the more likelihood that you have this kind of distortion and inducement in the next molecule. So the larger the molecule, the more easily it can be distorted. And so the really big molecules, so like gasoline, even though gasoline is considered non-polar, it's still a liquid at normal temperatures because they're such big molecules, and so they have really relatively strong dispersion forces compared to maybe some other molecules. All covalent molecules of any kind all have some London forces. Just happens that maybe if something's polar, the dipole may be more important. However, they still have London forces. So all molecules have London forces. And again, if you get a bigger molecule, they have a little bit more London forces. Okay, so this is sort of showing what I was talking about. So there's maybe in an instant, there's an unequal distribution of electrons. It forces the electrons to sort of move over here on the next molecule. So there's an instantaneous attractive force, temporary dipoles that then go away. Polarizability is another word that is used. Sometimes a polarizability is the measure of how easy or difficult it is for another charge to distort a molecule. So like if this molecule is highly polarizable, it's going to easily be affected by the neighbor. So if it's polarizable, it's going to sort of have these instantaneous temporary dipoles for a moment and then allow it to happen in another molecule. So that's just another word, polarizability. All right, so just kind of on the scheme of things, sometimes you hear the term van der Waals forces. Van der Waals forces are really just those dipole, and London forces. That's just another name for them. And then keep in mind, like I said earlier, hydrogen bonding is the strongest type of force, even though it's still an intermolecular force. It's not a true bond, it's just an interaction. Dipole are kind of middle, and then the London dispersion forces are the weakest. But again, all compounds have some London dispersion forces. All right, so we're going to come back to that, to those interactions, and talk about, so you can kind of imagine some molecules, you know, if you've got dipole interactions, they're going to have a stronger attraction than something that's just a dispersion force. And so that's why we have such differences between boiling points of different liquids. And we'll talk about more of that at the end of this chapter. All right, so again, this is something you probably learned in kindergarten or maybe even before that. What are the names of the state or the phase change when you go from one substance to another? So if you go from a gas to, let's start there. So if you go from a solid to a liquid, we know that's you're melting. And if you go from a liquid to solid, you're freezing. So you should know those names. I hope you do. All right, what about gas to liquid? All right, we know if we go from a liquid to a gas, we're evaporating it or vaporizing it. Either word is fine, evaporation or vaporization. And then going from a gas to a liquid is just called condensation. And then these you may not have learned in kindergarten, but you may have learned them somewhere along the line. What if you go from a solid to a gas? So if you take a solid and it goes straight to the gas, that's called sublimation. So you bypass the liquid state, sublimate. So dry ice is solid carbon dioxide, and at normal pressures in room temperature, solid CO2 will sublimate straight to a gas. And then if you want to try to take a gas and make it straight to a solid, that's called deposition. Every once in a while you might hear condensation for that too, but I try to use a different word so we don't get confused. So deposition, deposits, it deposits.